All right, strap yourselves in because today we're going deep on something that'll really mess with your view of reality. Wave-particle duality.
Ah,
Yeah, we've got some wild articles and even a simulation of that super famous double-slit experiment. It'll all help make sense of this brain-twisting concept.
you know what's truly fascinating about wave-particle duality? It just flips everything we think we know about how things work, like upside down. I mean, we're so used to particle or wave, one or the other, but get down to that quantum level and suddenly those lines blur,
It's like
man.
the universe is playing hide and seek with us, isn't it? Lights all wave-like when we're not paying attention, but try to measure it. Bam, particle city.
Haha, yeah, great way to put it. And it's not just some theoretical quirk either. This affects how we understand the entire universe down to its tiniest bits. Like electron microscopes, those things are using the wave part of electrons to see viruses, atoms, stuff we never could before.
It's like we're using the weirdness to peek behind the curtain of reality, huh? So to really grasp this wave particle thing, we got to talk about that double slit experiment. And lucky us, we've got this simulation to actually run it ourselves, virtually. Imagine this. Barrier. Two tiny slits got in it. Shine a beam of light through what shows up on a screen behind it.
Well, if light was just a wave like we normally think, you'd get two bright lines, one for each slit. Kind of like when you throw two pebbles in a pond, those ripples spread out.
Right, exactly. That's what makes sense to us. But here's where it gets freaky.
Yeah.
In the real experiment, no neat lines. Instead, you get an interference pattern, like bright and dark bands all mixed up, as if the light going through each slit is like messing with itself. It's going through both, somehow, then bumping into itself on the other side.
And that's only the beginning.
Hmm.
Now, crank that light source way down, so dim that only one photon, a single light particle, comes out at a time. You'd figure, all right, it's got to pick a slit, right? One or the other. But nope, over time, even those lone photons make that same interference pattern.
Hold up, so one tiny photon is interfering with itself. How's that even possible? It's like it knows both slits are there, even though it can only go through one.
That's the crux of this whole duality thing. A photon isn't just like a tiny marble shooting straight ahead. It's acting like a wave, spread out, with chances of being in different places at once. Only when we measure it, try to see where it lands, does it collapse and become a particle at a specific spot.
So until we look, it's this fuzzy cloud of maybes. And by measuring, we're forcing it to pick a spot. Does that mean we're like changing reality just by observing it?
That, my friend, is a question that's been bugging physicists and philosophers for ages, and that's where we're headed next. There are different ways to interpret all this quantum stuff, each with its own take on what observation really means and what reality truly is. Yeah, it really makes you think, what is real anyway? It's like we're tied into making things exist just by looking at them.
Totally mind-blowing, the idea that we're not just watching the universe, but like participating somehow. But how do scientists even approach this? Any theories out there trying to explain this wave-particle duality and how observation fits in?
Oh, yeah, there are a few big interpretations, each with a different angle on this whole puzzle. One of the most famous is the Copenhagen interpretation.
Okay, so what's that one all about?
Basically, it says when you measure something, that wave function, that fuzzy cloud of possibilities, collapses. It's got to pick a definite state. Like the particle was in all those possible states until we looked, then we force it to choose.
So it's like our measurement makes that specific reality happen. That's a pretty wild idea.
Yeah.
Any other interpretations that see it differently?
Oh, yeah, there are. And one that's really interesting is the many worlds interpretation. This one takes a whole other approach.
Lay it on me. What's the many worlds take?
All right, get ready, because this one gets kind of trippy. The many worlds interpretation says every time something's measured, the universe splits. Multiple parallel universes, each one for a different outcome of that measurement.
Whoa, whoa, whoa. Parallel universes. Are we talking like alternate me with a pet dinosaur or something?
Haha. Might sound like sci-fi, but the many worlds interpretation is legit in physics. It's saying all those possible quantum outcomes, they do happen, just each in its own separate universe, no crossing over.
I'm trying to follow here. So back to our double slit, one photon could go either way. Many worlds is saying in one universe it goes left, another it goes right.
Exactly. And there'd be tons more universes for every other thing that photon could possibly do, as long as it follows the quantum rules.
So instead of the wave collapsing, the universe is constantly branching out, making new realities for every little quantum event.
That's the gist, yeah. Pretty radical, but it's got some serious supporters in physics.
It definitely changes how you think about reality, that's for sure. So is there any way to prove or disprove these interpretations? Or are we just stuck with these mind-blowing possibilities?
That's the tough part about quantum mechanics, you know? hard to design experiments that can really tell these interpretations apart. A lot of them make the same predictions about what'll happen, even if their explanations are totally different.
So it comes down to which one makes the most sense to you, or which one keeps you up at night less.
Haha, there's definitely some of that involved. But physicists are always looking for new ways to test these ideas, poke deeper into the mysteries.
Fascinating and frustrating at the same time.
Hmm.
So we've been talking photons, light, but does this whole wave particle thing apply to other stuff too? Like, could you do the double slit with electrons or even atoms?
Great question, and the answer is yes. Scientists have done this double slit with all sorts of particles, not just light.
So they do the experiment with like atoms and what happens? Do they still get those interference patterns, even with something way bigger than a photon?
Yep, they do. It's really something else. Even stuff we think of as like solid atoms, molecules, they still act wave-like in the double slit.
So it's not just light being weird, it's like a fundamental thing about matter itself.
Mm.
So theoretically, could anything act like a wave, like a baseball, a car? Could you do the experiment with those?
Theoretically, yeah. But think about it. The wavelength of something that big is so tiny because they've got so much mass, It'd be impossible to see any wave effects with the tech we've got now. Quantum stuff, it really shows up most at tiny scales, atoms and smaller, where mass and size are super small.
So the wave part is there, but it's like way too small to notice in our normal world.
Exactly. Imagine trying to see the ripples from a pebble in the ocean, but you're miles and miles away. The ripples are there, but too faint to see from that far out.
Okay, that makes sense. So we've covered the double slit, how observation matters, these different interpretations. It's all pretty mind-blowing, to be honest. But I'm wondering, is there a bigger picture here? How does wave-particle duality fit into how we understand the whole universe? What's it really telling us?
That is the question. This isn't just some weird thing in a lab. It's woven into how physics works, like at the deepest level. It has huge implications for how we think about the universe, like fundamentally. And one of the key areas where this comes up is quantum field theory.
I've heard that term before, but honestly, not sure I get what it is. Can you give me the quick version?
Sure. Quantum field theory, that's our best description right now for how particles and forces interact, like at the most basic level. It's a way to put quantum mechanics together with special relativity and the idea of fields.
Fields, like magnetic fields, gravity, that kind of thing.
Exactly. But in quantum field theory, we take those fields and go even further. Instead of little point-like particles, we think of them as like excitations in these fields that are everywhere.
So it's like the whole universe is this giant web of fields, and particles are just little pops or wiggles in those fields.
Great analogy. And these fields are not just some math thing. They have real effects, like the electromagnetic field, that's responsible for light, electricity, magnets, all that.
Wow, so light, electricity, even the magnet on my fridge, that's all just this one field doing its thing.
You got it. And the fact that light can be both wave and particle, that comes directly from how the electromagnetic field works at the quantum level. It's all connected, man.
So wave-particle duality, it's not just this weird lab thing. It's built into the very laws of physics that run the whole universe. Pretty amazing and kind of makes you feel small, shows how much we still don't understand.
Absolutely. We've learned a lot, but there's always more to discover. Wave-particle duality is like a reminder. Reality is way weirder and more wonderful than we think sometimes.
Couldn't have said it better myself. And I think that's a great place to wrap up our deep dive into this incredible topic. For anyone listening who wants to go further, definitely check out that JavaScript simulation we mentioned. It's a fun way to play around with the double-slit experiment, actually see wave-particle duality in action.
Yeah, it's interactive, helps get those concepts really solid, and who knows, maybe it'll spark some new questions for you too.
Because maybe, just maybe, one of our listeners out there will be the one to make the next big discovery in this crazy quantum world.
Until next time, folks, keep asking those questions, keep exploring, keep diving deep into the mysteries of the universe.